Thank you. So nice to be back at UT and see so many friendly and familiar faces. Clicker. Okay. Okay, so we're going to go a little bit further up the supply chain. Daniel did an amazing job of setting up my talk, so thank you, Daniel. We're going to be looking at exploration and characterization of sedimentary basin lithium resources, or oil-filled brines. So first, I'd like to recognize my collaborators and industry sponsors. We are an interdisciplinary team of researchers that work on critical mineral deposits across North and South America. Kathy Gagnon's here today. Please go to her poster and learn about volcano sedimentary deposits as part of this team. And I specifically want to thank the industry sponsor who provided financial resources and brine samples for this project, E3 Lithium. So as Daniel set up so nicely for us, lithium production and demand has grown exponentially over the last 3 decades. This is predominantly in response to an increasing demand for lithium-ion batteries for applications such as electric vehicles and grid storage of renewable energies. The United States produces less than 2% of this global production as of 2023. So lithium resources globally, lithium production globally comes from predominantly 2 types of resources, as we've already heard today. Hard rock deposits like LCT pegmatites and closed basin brines such as those in the lithium triangle. The United States and its neighbor Canada has scarce traditional lithium ores, and so unconventional deposits are really important. So as I mentioned, predominantly, lithium brines produced and sold to market today are coming from these closed basin systems. We have one of these in the United States that's under production right now, Clayton Valley, Nevada. But the vast majority sold to market are coming from countries like Chile and Argentina in the lithium triangle of Central South America. Unconventional resources are going to be incredibly important for securing domestic pipelines of critical mineral resources like lithium. So these would be things like geothermal brines, which we've touched on already today, sedimentary basin brines, so brines occurring deeper than 1 kilometer at relatively low temperatures, under 100 degrees C, or oil-filled brines, like we're going to talk about today. So oil-filled brines, although they are lower in lithium grade or lithium concentration, they actually are on par in terms of lithium resource scale to closed basin brine systems. The brine we're going to talk about today, the Devonian Leduc Formation waters, are estimated to have over 16 million tons of lithium carbonate equivalent in situ in these reservoirs. So the Leduc Formation contains elevated levels of lithium in isolated dolomitized reef trend reservoirs, which formed in a pyric seaway in the Western Canadian Sedimentary Basin during the Devonian. These are encased in marine shales. And the Leduc Formation has been under production for oil and gas since the 1940s, and discussions around elevated lithium concentrations in the Leduc Formation have been ongoing in the scientific literature since the 1970s. It turns out that lithium concentrations across the Western Canadian Sedimentary Basin and Alberta are heterogeneous. So this is a problem for resource valuation, resource exploration, and ultimately production. So we're going to use a data set of dissolved species data and isotopes to try and understand why these heterogeneities exist and how we can predict them. So I'm going to show you a bunch of data from different isotope systems today that all help us understand the origin of these brines and the modification of these brines since their origin, as well as can speak to the possible lithium sources. So oxygen and deuterium isotopes are going to be useful for helping us understand fluid origins and mixing processes. The radiogenic strontium isotope data is going to tell us things about fluid mixing and rock-water interactions. And ultimately, lithium isotopes are going to help us speak to lithium sources and the role of rock-water interactions in sourcing lithium to these brines. Okay, so jumping right into deuterium and oxygen isotopes, the Leduc brines plot along an evaporation trajectory, which you can see if I can figure out the pointer. See here? We also immediately notice that these brines plot in regionally distinct isotopic trends. In the upper right-hand corner, your right-hand corner of the figure, you can see an inset map that shows these 3 regions that correspond to different levels of lithium concentration. Click back to the last slide. Just to mention that these northeastern brines, so this region here, show the highest average concentrations, although we have the least data there. The southeastern brines, this region down here, show moderate concentrations, but homogeneous. And that's what the 16 million tons LCE is based off of, an average concentration of about 74 ppm. And then these northeastern brines are significantly lower in lithium. So trying to understand that heterogeneity is the point of working with all these isotope systems in addition to dissolved species data. Okay, and there's been a long-standing hypothesis that the origin of these brines is related to marine waters because the depositional systems for the reservoir facies and source rock facies are marine. So we're going to test that hypothesis with isotopic data and elemental dissolved species data. So when we look at lithium and its trends with key dissolved species such as major ions and total dissolved solids, delta O18, we see a strong positive covariation between these indices, supporting a potential seawater evaporation mechanism for the formation of these brines and the origin of the lithium. But let's investigate that a little bit further. So we can see that the Leduc isotopic data lies parallel but offset to the expected isotopic trend if we were to evaporatively concentrate seawater. So what could be driving this offset? Possibly rock-water interactions with basinal sediments, so basinal carbonates, and specifically basinal shales. This is based on global compilations of isotopic concentrations. We can also see from the oxygen and deuterium isotope data that the northeastern brines, which are our lowest lithium concentration, approach the global meteoric waterline. So those are the squares that go down and to the left of the plot. And this indicates that these brines are likely diluted by meteoric waters. And indeed, we do see that these northeastern brines are the lowest lithium concentration values and have the lowest correlation between lithium and various dissolved ions. So to further interrogate how these brines form, we can look at chloride-bromide ratios. So chloride-bromide is a system that's very useful for distinguishing between a marine origin of connate waters, so waters that are buried with the sediments in the subsurface, versus waters that come from the dissolution of thick evaporite units. So there's a long-lived hypothesis that local dissolution of Devonian evaporite sequences, the prairie evaporite, might be the source of these waters in the subsurface. And so looking at these data, we can see that the brines from the eastern side of the basin parallel what we would expect to see in a seawater evaporation trajectory, but are somewhat offset and dispersed across that trajectory. This could be explained by meteoric water dilution processes. And then that the northeast brines are on the seawater evaporation trajectory to above. And so this data may suggest that these brines are coming from dissolved evaporite units. Okay, but regardless of how these brines form, if they have a marine origin, if we evaporatively concentrate seawater, can we get the lithium levels that we see in the brine today? And the answer is no. Even if we evaporate seawater up to potash saturations, which is, we have potash minerals in the prairie evaporite, we can't achieve the lithium concentrations that we have in the Leduc brines today. So we really need an extra source of lithium. So we turn to radiogenic strontium isotopes, isotope ratios. We can see right away that again, the Leduc brines plot into distinct geographic groups, with the northeastern brines showing more radiogenic signatures. These signatures overlap with late-stage dolomite cements that are interpreted to come from laramide-related fault fluids that tap deep basinal siliciclastic units. Whereas the northeastern and southeastern brines show much less radiogenic signatures, lower radiogenic signatures, overlapping with Devonian shales, carbonates, and evaporite concentrations, so suggesting that these brines never interacted with deeper, more radiogenic siliciclastic units. So what can all of this tell us about lithium sourcing? So we have to turn to lithium isotopes for this. So we have data only from the southeastern region to date. We're updating this as I speak. But the lithium isotope values plus lithium concentrations suggest that that shales undergoing elevated temperature, but not high temperature, rock water interactions with these brines may play a key role in controlling the lithium concentrations of the Leduc brines across the basin. And we also see that lithium covaries very strongly with potassium, suggesting that lithium may be sourced from clay mineral exchangeable sites during these elevated temperature interactions in the subsurface. So this leads us to a preliminary conceptual model for how these brines form and informs some recommendations for exploration and characterization in the future. So we believe that the Devonian Seaway of the Western Canadian Interior Basin was elevated with respect to lithium as compared to modern seawater values, and that clay minerals were able to capture some of this lithium in exchangeable sites within the Devonian shales. Then early burial compaction drives lithium-enriched pore waters, as well as secondary fluids from dissolution of older evaporite sequences into the Leduc dolomitized reef trends. And finally, across the basin, there's variable mixing histories and meteoric water dilution, which ultimately controls the lithium concentrations of the brines. So swinging back around to what does this have to do with these heterogeneous concentrations of lithium and how that is going to affect resource valuation, exploration, and production. We've been able to show that the Leduc brines across discrete reef trends are geochemically and isotopically distinct. This suggests that there's different formation mechanisms, different mixing mechanisms across the basin, which lead to higher and lower lithium concentrations. We now know that meteoric water plays a key role in diluting brines to the northeast, so those brines are somewhat less prospective, lower lithium concentrations. And we know that fault-related fluids are likely providing an additional source of lithium in the northwest, so a very prospective and interesting area to explore, especially in places where subsurface faults tap deeper siliciclastic basinal units. And we also are showing that the Devonian shales seem to play a key role in contributing additional lithium trapped in clay minerals to the oiled field brines across the Alberta Basin. We're now doing work to actually connect the brine chemistry to the solids chemistry in the Alberta Basin. So we're working through the geochemical and isotopic characterization of the Devonian carbonates, dolomites, and shales across the basin to understand the interplay between the brines and the solids. So finally, this has implications for where we should explore for lithium brine further in the Alberta Basin, and it also has implications for places to avoid exploration. And with that, I'll take your questions.